Optimize. A journey through database query optimization. This course is filmed on location at Carnegie Mellon University in front of a live studio audience.
Hi guys, so welcome to 1579, a special topics course on database systems. And so this semester's topic is going to be on query optimization. So instead of teaching 721, which would be like the architecture of database systems, this is really about how to build a query optimizer, which I would argue is going to be the most important part of a database system. So the goal of this semester is that you're going to learn the modern practices and the ways to actually go ahead and implement a database query optimizer. And the goal for you guys, that the outcome would be that, like, okay, you could sit down from scratch if you really wanted to, if you were crazy, and you could just build a query optimizer from scratch or modify an existing one. And as part of that, since this is doing databases, it's very important to make sure that the code we're writing is obviously correct, right? Because it doesn't help us if our queries run fast, but it produces the wrong answer. And as part of that, we're also going to do a lot of work on documentation and testing. These are soft skills you need to have in system development. So this semester, we're going to cover both the foundational materials in query optimizers. So next class, we're going to cover the OG, the original query optimizer paper from 1979 from IBM. But then as we go along, we'll build upon those foundations and start talking about the modern practice, modern implementations. All right, so you're already here, so maybe I don't need to convince you, but why should you take this course? There's more databases than ever. There's more money in databases than ever. Larry Ellison just became the third richest person in the world, and he bought a quarterback from the University of Michigan for $12 million, which is like a fraction of his net worth. Right? So a lot of money in databases. Everybody has database problems. Humans are not. Hey, what's up? Humans are not scalable. And the query optimization is going to be the key thing that's going to separate one system versus another. Like, we'll talk about Snowflake and other systems throughout the semester, but the basic architecture of Snowflake was invented in 2013, and pretty much every database system that does analytics is predicated on that same architecture. We covered a lot of those key things in the intro class last semester. So the thing that's really going to make one system better than another is going to be the query optimizer, right? If you can't generate a good query plan to run the most efficient way, then who cares how fast your engine is if it's going to do the stupidest thing, right? So from my perspective in research, the problem is very, very hard. I'm going to keep saying this throughout the entire semester. Query optimization is an unsolved problem, and I find it really fascinating because I don't know anything about it. And in industry, again, people will pay you a lot of money if you can do this well. The one thing, since I've been at CMU for almost 10 years now, when the database companies email me, they always say, oh yeah, by the way, do you have any student that's working in query optimization? Because it's really hard to find people with experience that work on these things. So again, I realize this is 799, not 721, but I just want to show you, here's some of the photos of the students have taken 721 and 799 over the years, and all the various places that they've ended up. And actually, well, I shouldn't say his name, but this person here, he's still here, and he's going to a new database startup called SpiralDB, right? So again, we'll cover Databricks, we'll cover Oracle, we'll cover Snowflake and stuff. Like, all of these people have query optimization problems, and all these people are basically writing query optimizers from scratch and want people to work on this stuff. So the background you can need for this course is, I'm going to assume that you've taken a introduction to database systems. Keyword there is in systems, not just like I've seen other schools database classes. They're not very good. But so if you've taken 1545, 645, or a one that's similar, then you would have the subsequent background. So we're going to plow right ahead, start talking about SQL, relational algebra, system implementation, storage models, processing models, all the things we covered in the intro class. We're going to assume you already know these things. We're not take time out to explain them. So this is also not an ML course. So occasionally, as we go along, there'll be algorithm, there'll be ML techniques. Won't be anything in LLMs, I don't think. That's still a little early for that, but there'll be some techniques going to be based on using machine learning. So we're not going to cover anything like, hey, here's like the machine learning algorithm they're using this and explain and prove that actually why it works, right? We just use whatever works. If it makes our database go faster, then that's all we care about, right? So I posted this right before class today. The course website is up. It's not complete, but the syllabus is there. So all the things we'll cover in the logistics discussion right now, all that's available on the course webpage. And then, of course, I'm going to say this multiple times, right? CMU makes a big deal about academic honesty. I make a big deal. So please make sure you follow the policy, including for AI, using AI for certain things, as we'll cover. And if you're not sure whether something is okay to do, please just email me, right? Because I'd rather have a discussion like, hey, that's a good idea, or that's crazy, don't do that, than doing something stupid and we have to report you later. Okay. All right, my office hours will be on Wednesdays after class at 3:30 in my office, or if you can't make that, by appointment. And then we can talk about whatever you want related to the class, just how to get database jobs, the projects that you're working on. I can talk offline about what's going on with Mushu in Chicago. I don't want to say anything publicly here. Still not good. But anyway, if you want to talk about these things, come to my office hours. We have one TA for the course over there, Wan Shan Lim. He's the #1 ranked database student at Carnegie Mellon University, a database PhD student. He is smarter than I am. He doesn't know yet. He'll graduate and then figure it out. He's also a certified chicken farmer. So if you have any questions about chickens, he hates chickens with a passion. But anyway, so Wan's helping us out this semester, and he'll post his office hours, and he'll be posting on Piazza as well. Okay? All right, so the breakdown for your grade is going to be a combination of the following. So it's going to be a reading heavy course. So we'll cover this in a second, but like every class, there'll be a reading assignment. And for some classes, as long as it's not the textbook, which we'll cover in a second, you'll have to write a review for this. And the standard, like, here's the overview of what the paper is about, 3 good ideas, 3 bad ideas, and then what workload are they using to evaluate it. We also have, I'm going to assign everyone to write lecture notes for every class except for this one, and when we do presentations. So the idea is I'll post a spreadsheet, put your Andrew ID and a date. If you want to swap, I don't care. I'm just going to randomly assign things. And the idea is that you would condense down the discussion we have in the notes, in the lectures, and condense it down into similar to the notes we had in 445. There'll be 2 projects I'll cover in a second, and then there'll be a final exam the last day of class. Again, so the reading assignments that when we post the schedule tonight, you'll see that for every single lecture there'll be a list of readings, and then one will be marked with this sort of crown icon, and that's the primary reading. That's the one you obviously going to cover in the lecture and focus on. But if you want to go beyond what the assigned reading is, there'll be additional papers as well. So you have to write a synopsis. You got to submit it before class starts. There'll be a Google form at this URL. That'll be active tonight, and you select the date. Just copy and paste the text field of your write-up and put it in there. You're allowed to miss 1 review per semester, and then the system will keep track of that. And then anytime we do an assigned reading for this textbook that I posted on Piazza from Microsoft, for this one, it's basically a survey of existing techniques, not really proposing new ideas. So it doesn't really make sense to do pros and cons of what they're talking about. Now, I didn't mention this too much on Piazza, but the reason why this book is a big deal is because for years, Microsoft has always sort of had what is considered in industry the best query optimizer. That's at least widely used. The Germans have an Umbra is also very, very good. And we're going to read a lot of paper from the Germans as well. But the Germans' approach is going to be a bottoms up, which we'll cover in a second. The Microsoft one is top down. And there hasn't been a good explanation of how to do top-down query optimization until that book came out in December. And then, normally you have to pay for the book, but I guess Microsoft bought it and gives it away for free. So you can download it without paying them, which is fantastic. Right? Microsoft has enough money. All right, so again, you use this Google form, and then you submit a review, and the first review will start on Wednesday's class. And again, please use your own writing, especially for the paper we're going to read next class. Right? It's from 1979. It's a very, very famous paper. There's a ton of write-ups about it. Please don't copy and paste. Write things in your own words. Right? This is an upper level class. You get the most out of it by doing the reading yourselves and doing the writing yourself. Right? You're not trying to cheat through me. Cheat on these things is really cheating yourself. Right? All right. So again, we'll have to follow the CMU academic policy for academic integrity. The lecture notes, as I said, again, be one. Every student will be assigned at least 1 lecture. And then the idea is that you just watch the video, or you and pay attention to class and understand the papers, at least covered, and you just condense down what was talked about in the class. And this is meant for both you and in your understanding of the course, for the other students taking in the class, and then for we put things out on the internet for free. People can follow along and follow the notes as well. So for this one, if you want to take the transcript of the lecture and throw that to ChatGPT and have it summarize it, by all means, do that. That's great, fantastic, right? So when you do that, just when you submit the pull request on GitHub, just say like, this is how I did that. So the way if others shouldn't say, hey, how do I do what you did to summarize this? They can follow your steps. And again, this is a it's going to go out with your name on it. So if ChatGPT starts hallucinating and says Andy helped invade Germany in 1943 or something crazy like that, right? You're responsible for that. So don't make sure you pay attention. All right. What's that? Oh, yeah, 44. Yes, thank you. Off by one. All right, the final exam will be a long-form examination, and that's going to be in class rather than the take-home one we did before. And I'll post more details of what this will be about, but basically it'll be not so much as you regurgitating ideas of all the things we talked about throughout the entire semester, but it's a way to sort of synthesize the thoughts and different topics we talked about and apply it to new settings, right? And that's best being done as an essay rather than and long form questions rather than multiple choice. So that'll be in the last day of class. So there's 2 projects as well. So the first one we'll hope to post online next week. The idea is that you'll start playing around with an existing query optimizer as a service. Calcite's probably going to be the one we're going to target because it's the most popular one. There's not very, give you an idea how hard this is. Like, there's not very many query optimizer as a services out there, right? There's 3 maybe, and one of them was written in 1998. Anyway, so the idea is that we'll give you a bunch of queries, give you a bunch of steps and rules, and you sort of play around this and see whether you can make queries run faster in InductDB. Yes. OpD++. Opt++. It's from Wisconsin. It doesn't compile anymore. Yeah. So these questions like, what's the third one? So there's Calcite from Apache. That's probably the most widely used one. There's Orca from Greenplum. That's only used by Greenplum. I don't know anybody else that uses that. And then Opt++ is out of the University of Wisconsin. But it was somebody's. It was Jignesh's office mate's PhD thesis. There might be another one that I'm not thinking of. Yeah. All right. Yeah. So again, the idea is here is to get you to understand what kind of transformations you can do, what the experiences are using something like Calcite, and this will be done individually. And the goal is like have it, play around with Calcite, try to get it to optimize a query that does as good or better than the DuckDB's query optimizer. Right, the DuckDB query optimizer is actually pretty good too. All right, and the last project, or project 2, will be about a half a semester long, a sort of a larger project with a group of people. And this is somewhere open-ended. Like you propose something because it's upper level graduate course. You propose something you want to work on within reason, within the scope of the class. And then the idea is that everyone works on these things and you present it. And there'll be a status update. So you would propose what you want to work on after the spring break, do a status update a month later, and then whatever our allotted time for the final exam during exams week or finals week, that'll be when we actually do the final presentations. And then if it's in the morning, we'll get bagels. If it's in the afternoon, we'll get pizza. But everybody gets a database shirt. That's my guarantee. Okay, and again, so please don't plagiarize. I post this because if anything comes up, I point to the video when we go talk to Warner Hall. And here's proof that I told you guys not to plagiarize. Okay? All right, any questions about the projects, reading assignments, or the note-taking, or the final exam? Yes? The question is what, sorry? Can you copy source code from other projects? Yeah, I mean, it depends what you're doing, right? Like, yes. Like if someone has a string copy function, you want to use that? Sure, I don't care, right? Again, within reason. Again, this is CMU, you're all very smart. So like, if you come to me and say, hey, look, here's my query optimizer as a service called Malsite, right? And it's clearly copied from Calcite, then don't do that, right? But if you use bits and pieces of Calcite and extend it to do something interesting that's relevant to the class, absolutely, go ahead, right? Any other questions? I mean, there's a chair here. It's not as fancy as the other ones. You good? Okay. All right, and the last quick warning I want to give to is that for the last 2 years, in the exact same week, the end of March, beginning of April, my daughter brings home, or my biological daughter brings home a stomach virus from the CMU preschool. And I've gotten diarrhea almost exactly the same time every year, right? And so this is probably going to happen again. So I just want to tell everyone a warning, like I may have to cancel class at the end of March. Not because I want to, because it's awful, right? So if that happens, we'll adjust the lecture schedule. Maybe we drop the Microsoft one, but like all the due dates for the projects and the reading assignments and synopsis, all that'll still be the same. Okay. And I can't not stress this enough. If you want to do databases, do not have children before you graduate. It is it's expensive and time consuming. It's at least 30 hours a week. All right. So the other thing we're going to do this semester, going beyond the course, is that we're going to run a new seminar series starting in beginning of February on query optimization and alternatives to SQL. So SQL has been around since 1974. There's been many attempts to kill it off and replace it with something else. All of them have failed. People are trying again now. Google has a paper came out last year called Pipe SQL, where they extended SQL to include pipes. The Germans have a replacement for SQL. Google has one, another one for, I think it's called Mellon. But there's a bunch of these things. They're replacements for SQL, or either they compile down into SQL. So we're going to have a combination of those guys giving talks, as well as database vendors come and talk about their query optimizers. I think MariaDB is putting out a new query optimizer, and they want to give a talk about this as well. So, this is optional, but if you want to go beyond the stuff we talk about in the course, obviously anything that's presented in one of these presentations, one of these seminar talks, wouldn't be on the final exam or anything like that. This is just exposing you to more of what is happening in the industry. Okay? And we'll post details about it later on. All right, so the last thing I want to also say too is if you took 445, 645, there's a lecture on query optimization, and I preface that lecture by saying that query optimization is the part of the database systems that I feel like I know the least about. And actually, it's one of the two parts. The first one is incremental view maintenance. You have like a materialized view. How do you apply an update to a base table and not have to recompute the entire view? I know roughly how to do that, but I don't know all the corner cases, and I wouldn't know how to sit down and build it from scratch. But query optimization is the other one that like I know the least about, because as we go along, it's very, very difficult and very challenging. So if you find an error in the lectures, either call me out as I'm talking, or if you're watching this later on YouTube and you find a mistake, there's an email there that'll go to me. If you find a mistake, just let me know and we'll correct it. Okay? All right. So with that said, let's get into a quick introduction to what the course material is going to be. The course is going to be about, and then that'll segue us into next class when we actually talk about early implementations of query optimizers, and then we'll build upon that to see more complex approaches. All right, so it should be sort of obvious to anyone again who's taking a database class of why we need a query optimizer, why we need query optimization. So query languages like SQL are declarative, meaning the application or the user is telling the database system what answer they want to get returned, or what answer they want the database system to compute on their data. And they don't specify anything about how to actually go ahead and compute it, right? So like a procedural query would be, hey, here's my for loop, and then here's my if clause for my filter, right? That would be telling exactly the algorithm you want the data system to use to execute that query. So instead, in a declarative language like SQL, you just say, hey, I want this answer. You care, but you're not really, you care in the end, because obviously if it's crappy, it's slow, but like, you're not saying like, I want this thing to be done exactly this way. You're just saying, here's my query, please go execute it in the most efficient way that you think is possible. And so the magic of database systems, or relational database systems that support SQL, is that they're going to try to find a correct execution plan for your given query, potentially without any prior knowledge about having seen this query before. And it's going to try to find the one that has the best cost. Now, cost is going to be something relative that we'll discuss throughout the semester. But the key thing, of course, there is going to be correct. Like, who cares if our query reads from dev null and produces no results? It's going to be super fast, but obviously it's going to be wrong. So we want to understand the semantics of what queries actually are trying to do as specified through SQL, and then try to find the best alternative choice for running the query in the most efficient way. So this is basically this sentence here. This is what this course is entirely about: how to do this, right? And do this quickly and do this efficiently, and obviously do this correctly. So the cost idea, again, we'll cover this in a second, but it's not going to be something that's tied to the real world typically. It's not going to be like a wall clock time, right, or a number of seconds. Right? It's going to be some internal metric that system is going to use. That's going to be a proxy for saying this query plan is more efficient than another. So say we take this query, and we want to talk about what the query optimizer can actually start doing to improve performance, and why you want a query optimizer to figure these things out for you, because the performance gains you can get are actually quite significant. So say that we have 2 tables in our database. We have departments and employees, and we're trying to find all the distinct employee names of employees that are working in the toy department. So in our catalog, we'll keep track of what indexes we have, whether they're clustered or unclustered, and a rough approximation for the number of records we have and how many pages we have. We'll also see later on that there actually can be additional metadata or summarizations of what's in these tables, what's in our database, that we're going to use to try to figure out the cardinality estimations or selectivity of predicates. So not just we're keeping track of like, I have 500 records, we're also going to keep track of like, okay, for these 4 attributes, here's the distribution of values that I have, like in a histogram or something like that. So if we take a naive or almost a literal translation of the SQL query that we're given and convert it into a relational algebra plan, a relational algebra tree, we would end up something like this, right? At the bottom, we have our scans on employees in department, and then we're doing a Cartesian product on them, which is the worst thing we're going to do. But in base relational algebra, that's what you do, right? And we'll want to fix that later on. So say we have some basic numbers we're using from our catalog, right? That we're going to do 50 plus 50,000 reads, and then we're going to write out a million writes, do a million writes out the disk to do a temp file, assuming that's the match after the Cartesian product, right? Then in the next stage, we're going to read all those writes back in, and then do our filter, or to do the join, write that back out, then do another filter on department name, write that out, and then do our final projection to for our final result, right? So again, in this case here, for this sort of, again, it was an exact or literal translation of the SQL query into relational algebra. For this example here, for this database, this query would take 2 million IOs. And say IOs is going to be our cost metric to determine whether one query plan is better than another, or what the cost executing query is, right? How much disk IO did I do? Well, there's a bunch of optimization we can do since we know how to speed things up from the intro database class, right? We know that we never want to do a Cartesian product. Instead, we want to do an inner join, right? And you're basically pushing down the filter to match from one table to another inside of the join operator, right? And now we can also be smart and say, oh, we're going to do a page nested loop or a block nested loop join. And then that reduces the amount of, we still read the data in, but now it reduces the number of writes down to 2,000. Then we do our additional filter and our projection, and now we got it down to 54,000 IOs. So the query optimizer's job is to recognize, going back here, that this Cartesian product is a bad idea. It's going to be slow, and so go ahead and substitute it with with an inner join. And then again, it produces the same result. So it's semantically equivalent, but it's much, much more efficient. But there's other optimizations we can do, right? Right down here, we spent so much time talking about the different join algorithms in the intro class. Well, we know that a page nested loop join may not be the most efficient thing. Instead, maybe you want to do a sort merge join, right? And now we go down to 54,000 IOs to about 7,500, 7,100 IOs. Again, by just swapping the join algorithm we used for that inner join from one algorithm to another, essentially we're changing what the physical operator we're using to execute the join, right? We reduced the IO quite significantly. And again, we can go further. We can do additional optimizations. Say in this case here, we were using the materialization query processing model. So at every single stage, we're letting the operator run to entirety, writing out all its output to a file, and then when that operator is complete, then we move on to the next one. Right? So this is the worst case scenario for some queries because we're not doing any pipelining at all. Right? We're executing one operator after another, just writing everything out. Well, if we switch this to a vectorization model, then we can take advantage of pipelining, where now we don't have to write things out the disk. We just pass a vector of tuples going up, and now we've reduced our IO by half. Now, in most of these systems, the query optimizer is not going to say, oh, I'm going to use a materialization model and switch it to vectorization. But I'm just showing you that, like, again, if you change what physical operator you're using or the overall strategy of how you're going to execute these query plans and something the optimizer can figure out for you, you can get a pretty significant reduction in IOs. Again, there's more we can do, right? Well, when we talked about join algorithms, we made a big deal deciding what was going to be the inner table versus the outer table, right? So we could swap these, and that might change things. And then, of course, we have this filter up here on the department name that we're doing after we join. We know that's inefficient or wasteful because now we're joining all tuples in employees in department, and then we just filter out the ones that are in the toy department. But if we push down that, if we push down the filter below the join, now reduces the number of joins we have to do, because the join tuples we have to consider. The join's always going to be the most expensive thing. So if we just, again, swap the order of this, move that down, right, and then run our query plan, right, now we're getting it to about 37 IOs. So we went from 2 million from the naive case down to 37. So this is why query optimizers are super important. And this is a trivial example. Like, you could write some if-then else rules to figure this out. But when you start having dozens of tables or even hundreds of tables, and with CTEs and nested queries and all these other nasty things you can do in SQL, then this becomes really, really hard to do. And how to figure out how to move things around without producing incorrect results. So the overall architecture, the thing that we care about in our database system, or the pipeline of how queries are going to come to us and what we're going to do this semester, is that, say again, our application is running some user code, JavaScript, PHP, Python, doesn't matter. They're going to send us a SQL query. The first thing that's going to hit in the database system is the parser. And this is going to be looking at the grammar of the SQL dialect that it's supporting, and it's going to break up the query, the SQL query, into tokens, and usually represent it as an abstract syntax tree. But it literally is just the string tokens, like select, from, table, and so forth. So now in the next phase, we take that abstract syntax tree, we pass this into what's called the binder, sometimes called the resolver. And this is the thing that's responsible for looking at the tokens in the abstract syntax tree and then mapping them to actual database objects. So like for a given name of a table, what's an internal identifier or object ID that tells me here's the actual table that they're referring to? Or if they're referring to a table that doesn't exist, the binder could throw an error. So every database system is going to maintain this thing, what we'll call the system catalog or the catalog. It's the database about the database. It's the metadata about what tables you have, what columns they have, what their types are, any additional views, whether they're materialized or virtual views, triggers, and all additional things. When you call, create something in your database, it lands in the system catalog. And the binder is going to produce what now a logical plan. It's almost like almost an exact translation of the sort of annotated syntax tree and then converting it to like a relational algebra version of it. But it doesn't say exactly how to execute anything. It just says, hey, I have these tables, I want to scan it. I'm not saying how to scan it, I'm just saying I want to scan it. I want to join those two tables. I'm not saying how to join them, I just want to join them. And that's the logical plan that then goes into our query optimizer, who can then also leverage information that's in the catalog for like what the schema looks like, to make decisions about how to, whether join one table a certain way versus another, or how to scan a table. And then there'll be this other thing we'll call a cost model. And typically it's embedded inside the optimizer, not always a standalone component. But this thing is responsible for getting the statistical information about what's in your database, like how many tuples you have, what the distribution of values look like, using some internal formulas to then figure out for given operations or operators that are in your query plan, what's the expected cost of them. And being vague what cost is, but we saw the example just before about we're using IOs to determine whether one query plan was better than another. The optimizer then crunches on this for a while, and then it spits out a physical plan. Again, that's defining exactly how to execute the query. And then it goes off and gets executed, right? So the thing we care about this semester is this piece, the optimizer, the cost model, and the cost model. The binder just engineering. It's boring code, but it's important, but you don't really do any optimizations there. And then, we can talk a little bit about how to get the schema information and statistical information in the catalog. again, this is repeating what I just said, but like the idea is that we're going to take a logical query plan that's going to come from the binder, and then we want to convert this into a physical execution plan. And our optimizer, we want to design it such that we can consider a large space of possible query plans we could execute that are semantically equivalent to the logical plan we were originally given. And then we want to be able to have a cost model that can determine whether one plan is better than another, right? Without actually having to run it. Because obviously, if you could run, if you want to know whether a query plan is fast and you have to run it, then that defeats the whole purpose of trying to figure out what's fast before you run it. Now, there'll be one query optimizer we'll cover at the end of the semester that does actually just go ahead and runs it. Want to guess what it is? Yes, it is MongoDB. Right? So what they do is basically say, all right, I don't know what to do, just run them all. Whatever comes back, that's the one they pick next time, right? And the paper just came out in December. The number one researcher in Australia sent it to me. They just wrote it, and lo and behold, it doesn't actually work in MongoDB. But we'll cover that later on, right? Because they don't have a cost model. They don't have a query optimizer. All right, so again, the idea is that we want to be able to determine whether one query plan is better than another, but actually I'm going to run it. And then we want to be able to efficiently search the solution space of possible plans we could have to narrow down and land on the one that has the lowest cost. And then we have a bunch of different ways we can do this that we'll cover throughout the semester. And some of the cool things you can also do is like reuse information you've seen from running other queries and help you make better decisions in the future. Or instead of generating a new query plan from scratch, like all at once, maybe use bits and pieces of other query plans that have run before, and you stitch them together to make a better query plan, right? And the fascinating thing about all this is that, again, through SQL, because it's declarative, you can just keep refactoring and improving your query optimizer, making it better and better, and they don't have to go change any of their application code because it's just SQL. They upgrade to a new version. Ideally, the query plans get even better. Doesn't always happen, and we'll talk about how to handle that. But like, again, instead of having to say, oh, here's this new API for your procedural query plan, you have to call it if you want to get all the new improvements of our new database system. The query engine, the query optimizer can just do that all for you without changing application code. That's a very powerful idea. And it wasn't obvious in the early days of databases, the 1970s, that you could actually even do this. Okay. We've already covered this before. I just want to say it again, right? We're making a big deal about logical query plans or logical operators and physical operators. The logical is a way to express at a high level what you actually want to do. Like I want to join table A and table B, but you're not specifying what actually join algorithm you want to use. Whereas the physical operator actually specifies what algorithm you want to use because the data system has to actually be able to support it and actually run it for you, right? And we'll see how we do all these transformations. I'll spend a whole class on doing transformations. We'll be able to go from logical to logical operators. Sometimes we'll like, join A and B will be a logical operator. We can convert that to join B, join BA. Right? It's a logical to logical transformation. But then you can also go from logical to physical. So join AB would be a logical operator, but then hash join AB would be the physical operator. And you don't go back the other way. So you can go logical, 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 physical, but you wouldn't go physical back to logical. Because you're losing all the information you've gained from deciding how to join it. We'll also see this too, that there'll always be a one-to-one mapping between logical and physical, meaning if I have a logical operator, I may actually break it up into two or more physical operators, or I may have multiple logical operators and I may coalesce them into a single physical operator. Right? If I want to do a join a table and then do an order by on it, well, if I do it a sort merge join, I can take the logical order by the logical join and condense that into a single physical sort merge join. So again, we'll see a bunch of these transformation tricks as we go along. So this is the rough outline of what we're going to cover throughout the semester. So we're going to spend the first quarter to third of the course talking about the actual implementation of the query optimizer, right? The search algorithms we're going to use to enumerate different query plans and transform, build up the plan to produce something we can actually execute, and the different kind of rules we can apply to change things. Then we'll talk about how to make this parallel and run these things, run the search for a single query across multiple nodes or multiple cores, or even multiple nodes. Then we'll talk about how we rely on the statistics to summarize what's in our data and use that to make estimations about how many tuples an operator is going to produce, because that's oftentimes going to be the thing we care about the most, right? Because I want to do the most selective joins at the bottom of the query plan as soon as possible rather than later, because it reduces a bunch of wasted work. Then we'll see also too the tricky problem of how to handle parameterization. Meaning, what if I have a query where instead of having actual constant values like ID equals 1, 2, 3, I have ID equals $1, because that's an input parameter someone's going to give me later on. How do I do query planning on that if I don't have the full query yet? Right? That's hard. Then we'll see how to take feedback from when queries runs and feed that back into the system and improve additional query optimization. How to actually also then adapt queries while they're running or while we're doing planning. If we see multiple iterations of the same query, how do we adapt that and make it go better? And then the end of the semester, we'll spend time reading papers from actual real-world implementations of query optimizers. There's not just the Microsoft book will cover what Microsoft does, but we'll read about Orca, Calcite. There's another Microsoft one, and then the MemSQL single store and MongoDB. Okay? So again, the next class, and we're going to really start hammering on this, because this is going to be sort of set up everything we need to know about how we want to actually build the query optimizer. And at a high level, there's basically two approaches. First is just to use heuristics or rules, and these sort of like hard-coded if-then-else statements, if you will, that say, if I see this pattern in my query plan, go ahead and apply this transformation. Like if I have my Cartesian product and then a join clause in a filter above it, I could have an if-then-else clause that says, if I see that pattern, just collapse that down into to an inner join, single operator, right? And so some database systems and a lot of when you see a first new database system coming out, this is probably all they're going to have, right? Because to build this one is very tricky. That's why this whole course exists. But like to do this will maybe get you up and running very quickly, but obviously long term this is going to be problematic, right? This is what Oracle did. No offense. This is what Oracle did for almost 20 years, right? They didn't have a cost-based search until like the early 90s. And what they would say is, oh, we have what's called a semantic optimizer. So they couldn't figure out the join order of tables in a query based on costs. They just said, oh, it's the order that they showed up in the SQL string. That's the order we're going to pick. And they called that a semantic optimizer. And they somehow, Larry Ellison said that was better. Right? It was all BS. But they eventually did this, and theirs is much better now. But like when most systems get built the first time, this is all they have. All the NoSQL guys from the last decade, they made a big deal not supporting SQL. Right? But a lot of it is because they didn't want to build this thing. They didn't want to have a query optimizer. They just said, okay, I'll give you a really simple a query API where you tell me exactly what you want me to go look up and how to get it. Right? And then after the fact, they've all the new SQL systems, including Mongo, have since added SQL. And they've had to build something like this. Sorry, they had built something like this, except for Mongo. But we'll cover that later. All right, so the idea here is that you do some initial transformations that are quick and easy to do, and it's either if the system only has a heuristic optimizer, then that's it. That's all you get. Like here's my query plan, go run it. Like this is the optimizer. In other systems, they'll do this to help prune out things they're going to be useless in this. Like I'm always going to want to do a predicate pushdown. So why do an expensive search transformation for this in a cost-based search? Just do it as a quick if-then-else statement. Apply the rule, and then go ahead and then do the search. So the cost-based search, again, is something like, think of like a classic search algorithm that's going to try to find something with the minimal cost. And ways to prune paths and branches if you know things are not going to be helpful or not, right? So the idea is that we're going to spend a lot of time on how to do this efficiently, but we also want to understand how to do this, because if you do this correctly, then it makes this go faster. Postgres does a combination of both. Right, but theirs is really hacky because there's a bunch of if-and-else statements that you have to make sure that the query plan ends up in the right form before you feed it into this. And then after you do this, then there's a bunch of if-and-else statements to fix the query plan to put it back in the form they can actually execute it. So the Postgres query optimizer, for much of the love Postgres, it's not a good implementation. Okay, we'll cover that later. The two big things that we're going to care about the entire semester, and you'll see this already on the schedule, is this dichotomy between top-down versus bottom-up search algorithms or optimization implementations. So bottom-up implementation optimization would be you start with nothing in your query plan, and you start iteratively adding physical operators to it to get you to your end goal of the final result that you would want for the query. So if I'm joining ABC, I would start with not joining any of them all, and then figure out whether I want to join AB first or BC first or whatever. And then once I figure out that level, then I go to the next one and add the next join operator I would need. You're sort of building things up as you go along. The other approach is going to be top-down optimization. And with this one is you start with the outcome that you want. Like, here's my final result of joining A, B, and C. And then you now traverse down and do transformations to add back in the operators you need to get you that result that you want. And I realize me standing here in front of a PowerPoint slide and making hand gestures that don't mean anything. This make more sense next class. But this is going to be the big thing that we're going to spend most of our time talking this semester, because the Germans and the IBM paper will be next class, and a lot of other systems are going to do this approach. The Microsoft book and a few other systems like Orca are going to do this one. And the guy that invented this one, right, in Volcano and Cascades, he said if you had to do it all over again, you start with this, and then you do this, right? You actually want both. So we'll spend a lot of time talking about what this means and what are the implications for the efficiency of the algorithm, how to do costing, and the complexity of the different approaches. And so again, going back here. So the paper you're going to read next class will be the bottoms-up approach, dynamic programming approach, or they're both dynamic programming. It'll be bottoms-up approach. It's the original one from IBM. And then after that, we'll read Starburst, which is the follow-up work from IBM that built upon the System R optimizer. We also need to understand what the objective function is for our query optimization. Like we sort of showed IOs, right? That's usually, again, a good proxy or a placeholder for something that's going to correspond to response time or latency of a query, but not always, right? And so there's a bunch of different things we have to consider when we, in some systems where you could ideally plug in and say, I want to minimize this, or I want to maximize this objective function, that metric. And the search algorithm essentially is the same, but now you have a different calculation to determine whether you're making the query plan better or not as you do transformations and as you do the evaluation of different options that are out there. And as I said before, we can't just go ahead and run the query, except Mongo does. Like, you can't just go run the query, see whether it's a good idea or not, because if you're considering thousands or tens of thousands of query plans, right, and the queries could take seconds or minutes to run, this is just not feasible. So we're going to rely on a cost model that's going to help us determine whether we think one query plan is better than another. Right? It'll come out to being like a single number. We can say, is this number less than this number or greater than this number, to determine whether one's better than another. But we can't take any calculation or estimate we get from our cost model, from our database system, and then apply that to another system. So Postgres has its own cost model. It produces a number that says this is the expected cost of a query. I can't take that number and go compare it against MySQL's number, because it can be completely different. It's just internally for us to determine whether one's better than another. And then we'll see some examples later on where in some systems they'll keep the best query plan and the second best query plan. And then for their own internal testing, they'll run both of them multiple times and see whether the cost model is actually accurate or not. Right? If your cost model says this one query plan is better than another, when you actually run it on the real system, ideally you want to know that that's actually true. So we'll talk a little bit about how to test that and figure that out. All right, the last thing I want to talk about is just somebody came back in your mind, but we're not going to touch too much on this during the semester, is that in all my examples so far, and most of the papers, almost all the papers we're going to read this semester, it's all about optimizing a single query. Now, you may see that same query multiple times over and over again, and there's some optimizations, or we can leverage the knowledge we gain from one iteration of that query to the next. Right? But in general, the optimization search algorithm is looking at one query, right? And you assume that it's running in isolation of other queries. Not always true, but that's typically how these things work, right? There is a line of research done on what's called multi-query optimization, or MQO, where you're given a batch of queries that the application is going to want to execute at the same time, either simultaneously or one after another. And the goal here is to then figure out, okay, what is the globally optimal query plan for all the queries that's going to have the lowest cost for me and going to be the best performance. And depending on the execution model of the queries, meaning are they running simultaneously or one after another, in some cases you actually could combine the queries, right? Instead of running two separate queries that run the scan on the same table, just do one query. And the data system could then split out the results according to who actually needs them. So you can do like result sharing and scanning, or scan sharing as well. So this is way more complicated. Obviously, the search space is way larger. As far as I know, no commercial system actually does this. This is only in research. But it doesn't mean like, it doesn't always have to be the case. So this might be like a project 2 idea. Like we could play around some ideas about like actually how to apply Calcite or Orca or our own system to solve this. Right? All right, so this is really all I want to cover for today. Hopefully, I keep saying this over and over again, that this is super, super hard. It's proven to be incomplete for the overall query plan. I think choosing join order is NP hard, right? So in my one example before where I showed like if I picked the worst query plan, I was doing 2 million IOs, and I picked the best query plan, I think it was down to 37. That's actually super common in the real world, where like if you get the join order correct, like we're talking orders of magnitude faster, like 10,000, 100,000x faster, if you get the join order correct. Now, obviously, if you get it wrong, then you pay the penalty, right? Queries can take days. Less common in the modern era, but in the old days, and like even the 2000s, it was not uncommon like queries would take a week to run, right, before column stores, right? So getting the right query plan, the best query plan is super important. Despite the name being a query optimizer and the course being about query optimization, we're almost never going to find the optimal plan, right? It's just sort of impossible. And in some cases, in like lakehouse systems or in the cloud, you may not have any statistics for your data because you've never seen the data before. Like someone plopped a bunch of Parquet files or CSVs in S3, you don't know what's in them, but they're asking you to run queries on them. How do you do query planning in that world? And that's where the adaptivity stuff that we'll see later on can help mitigate. Like I'll make a good best effort, but if I get it wrong, maybe I'll try to adjust myself as I run, or have triggers in my query plan that the optimizers can put in place to say, if I'm assuming the data looks like this, if it doesn't look like this, break out and let me know so we can run the optimizer again. Again, we're almost never going to be able to find the optimal plan. And so we're going to have to use a bunch of techniques that we'll cover that semester to try to guess what the real plan cost is, and then try to minimize the amount of compute time we're spending on in a search. Okay? Any questions? Yes.
Way back up, you said the Cascades guy, he wanted to do top-down first and then bottom-up. Hey, what did he mean by that?
So his question is, let me go back. My mouse doesn't work anymore. Okay, go back here. So not next class of system R, the next class next week, Wednesday, because Monday we're off, that'll be Starburst. And then the following week, we're going to read the Volcano paper and the Cascades paper. And so the same dude, this guy Gertz Graffi, invented both of them. So in 2018, he won the Test of Time Award at Sigma. And he got on stage, and he's done so many things. It's hard to cover everything. But he was talking about how he invented Cascades. He got hired by Microsoft to go implement Cascades in the SQL Server. And then he basically said, if I had to do it all over again, he would start with Cascades to do the initial transformations of the query plan, but everything except for join order. Then when you want to do join order, you do the German style, the hyper style dynamic programming, which we'll cover with the hypergraphs later on. You do that just to pick the join order.
Still bizarre to me how you can be like more efficient.
Yeah, the join ordering algorithm, doing right, more background for him. Like I like the Cascades approach, and you'll see this in the Microsoft paper, because to me it logically makes sense that you can define these rules, that it's a single unified search space, that you just kind of throw all the rules in. You have a way to set priorities to explore certain parts of the query plan or do certain transformations earlier rather than later to try to converge to a optimal query plan as quickly as possible. So I like that model, but it is, at least my understanding is, it's inefficient to do join ordering because you're kind of doing the same transformation over again, and the search space explodes. In the case of the join ordering algorithm we'll see from the Germans, it's just doing join ordering. So you've already done the transformations to do predicate push down and all the things that get it roughly into the right shape you want, where you know that there's rules that you always want to apply. Then they kick off the join search algorithm that's doing a bottoms up approach, and that's like super efficient. But we'll read that paper, we'll read the follow-up paper they have for this, and then there's a rough, I'm not saying it's as good as the German one, but there's a top-down approach to do join ordering that we'll cover as well. That goes beyond Cascades. Obviously, also too, the Cascades paper, I'm not gonna have you guys read it. This is why the Microsoft textbook is a big deal, because this paper is useless. Well, not useless, but like it's not as bad as the Paxos paper from Leslie Lamport, right? Where like you can't actually do anything with it, but like it makes a big deal about being object oriented, because that was the hot thing in like 93, 94, right? So it makes a big, like, so you read the paper and like you can't actually implement anything of it. So then the only other sort of good explanation of what Cascades is actually doing, because Microsoft didn't publicly talk about what they had, right? They would write papers about how to do a nesting and different aspects of the optimizer, but they never had a good description of here's the end-to-end implementation of it until this book came out. So the only other good explanation of what Cascades was this guy's master's thesis from like 1998 at Portland State University, that there's one chapter that describes here's what Cascades is, but even that's like not fantastic. Whereas like there's a lot of papers on talk about how to do this. I forgot the point I was trying to make. Yeah, so he wrote the Cascades paper. You can't read it. Well, you can read it, but like you can't take it and actually build anything. The Microsoft book actually is useful for that. And it's fantastic. Okay, anything else? All right. Again, so next class on Wednesday, we're going to talk about the System R optimizer, like again with the original implementation. We'll actually spend a little time also talking about the even early optimizers from Ingress. I don't think there's all I know about the Oracle one I've already told you, where like they lied and said, oh, it's great because the order of the queries that appear, the order of the tables that appear in the SQL statement, the string, that's the order they would choose. I think that's the only paper they really had for the query optimizer until they rewrote it in the 90s. But we'll talk about some of the early optimizers as well, and then for the System R. And then this will go live tonight, but there'll be a Google form again. You just submit your reading view there. Okay?
Matter of fact, hold the cup. This is like that wood grain type of shit. Shout out to Blockhouse, my dogs. Catch one, Big Al, Mike Strokes, Gumby, all that minds. I'm not the one who be amping up the weak ass rhymes. If you spit, if it don't rip through your mind with a sweet anticipated, orchestrated punchline like a reverse the hands of time. Get you captivated quick with the bullshit. I keep the Cadillac equipped for the long trip. I got the remedy for bitches when they start shit. Surround sound like I make them hoes fuck quick and suck dick. Crown me as the thug from the gun. Shit, some niggas claiming never rapping is sudden. Don't push the button, yes you motherfuckers in front.